The OSI transport layer. One of the most critical decisions when developing a network protocol is deciding between connection-oriented and connectionless methods of transmission. The transport layer is where this decision is carried out. In this nugget, we're going to define what a connectionless protocol delivers. Then we will look at connection-oriented protocols and how they're implemented at the transport layer. Next, we will break down key flow control methods, and we'll end up by looking at the error recovery process. The connectionless method of data delivery is analogous to first-class mail in the U.S. Postal Service. In our diagram, you see me mailing a letter in hopes that it gets to the final destination. I'm going to go to my local post office, drop the letter in a mail slot. As soon as that letter drops in that mail slot, I have to trust that this entire path through the U.S. Postal Service is going to take my letter and deliver it to the final destination. If it does not, I won't know. This is the trust factor. The same is true with connectionless network protocols. If I'm at a PC, N1, and want to deliver data with a destination of N2, if I'm using a connectionless protocol, I will release that data onto the wire and have to trust that the internet and every router in between is running optimally and delivers that packet to N2. If it doesn't get there, I won't have a clue. That's to say, any router, any link in this path discards this packet, I won't know that it didn't arrive at N2. So as you can tell, for data to be transmitted over a connectionless protocol, one of two things has to be true. Either that data has to be trivial enough that if it is lost in this path, it doesn't matter, or the second option is that this network is running so well that there are no errors and there are no discards. I hope you're laughing as hard at that second option as I am. There's no way we're going to find a network that is running that solid. I'd venture to guess, unless it is two PCs directly connected, that won't be true. So you got to imagine that the first option is more likely the case. This data is considered trivial, and if we lose that data, it has no bearing on our performance or has little bearing on the overall performance of our network. To drive that point a little further, we're going to look at the header of a UDP packet. UDP is a User Datagram Protocol. And what it is it's the connectionless method that is invoked at the transport layer whenever we're using TCP/IP. So let's take a look at the packet. We have only a few fields. The first is the source port, then the destination port, the length, the checksum, and the data. There's not many fields. But let me stop for a second. Source port and destination port. This may be new to you, so let's get an explanation as to what that is. The analogy I'm going to use to explain what a port is P.O. boxes at a U.S. post office. P.O. boxes, a bank at different post offices, the United States Postal Service representing the internet in UDP traffic. All right, so I have a sender, and this is going to represent the computer. This bank of post office boxes is N1. This bank of post office boxes is N2. I have a sender that sends a message out through the U.S. Postal Service, through the internet, and it arrives at a specific port. Now these ports are analogous to a specific P.O. box. Now if that P.O. box is owned by an individual, then the letter will be placed in that box and the individual can retrieve that piece of mail. Now if it's not, if that is an unowned box, what the U.S. Postal Service will do is simply drop that letter if it doesn't have a return address. In the connectionless protocols, essentially that's what we're dealing with because it's not going to be returned. It just goes to the bit bucket. Now back to our UDP header. So we have a source port and a destination port. We have a length that gives the overall length of the packet. We have a checksum. The reason there's an asterisk there is because this field is optional in connectionless protocols, specifically in UDP for TCP/IP. Now what does that mean to us? That means that even if this packet were to arrive through the internet and arrive at N2, it doesn't have any type of field to say that that information was not altered. And N2 can trust that information even though it says something completely different than what I initially intended it to say. This is true because the checksum is a mathematical algorithm that takes into account the header and the data, each bit in the data. And it comes up with a checksum. It transmits that number across with the packet until it arrives at N2. When N2 receives this packet, it does that same mathematical algorithm, taking into account the header and the data. But let's say that this 0 bit was now changed and it's a 1 bit. The checksum that N2 comes up with is going to be different than the one that N1 came up with. and that's going to tell it that something has been altered. Don't trust this data. Luckily for us and our data, another method of data transmission exists, and that is the connection-oriented method. This method is analogous to certified mail rather than the regular mail. Again, I'm going to go to a post office and deliver a letter. This time what I do different though is I fill out a card and I check the box that says I want a receipt for when this mail is delivered to N2. So now the mail traverses the U.S. Postal Service as it did in the first example, arrives at the final destination, but the bonus here is now I get an acknowledgement that it was received. The same thing is true for connection-oriented protocols when we deal with the Internet. N1 is going to send a packet across the Internet. N2, upon receiving that packet, is going to send back an acknowledgement saying, I received the packet. Now, if that packet is dropped anywhere in this process, I won't receive an acknowledgement. But I have a trick that I'll show you later that shows me that even if I don't receive an acknowledgement, that is information. So no news in this case is news to me. As we did in our previous example, we're going to take a look at an example header that comes from the transport layer from the connection-oriented side of the house. So TCP, which is Transmission Control Protocol, is a connection-oriented method of delivery for TCP/IP at this layer. So let's look at what we have here. Again, we have a source port and a destination port. Underneath that, though, these are the new fields. We have a sequence number. We have an acknowledgement number. We have the length, as we had earlier. This is reserved and blank for now. We have some flags. We have a window size, the checksum, which is used in TCP on a mandatory basis, an urgent pointer in case this information is very, very urgent, options for even more options to be built in to this connection-oriented protocol, and the data. Let's take a look at how the sequence and acknowledgement fields are used. Here we have a diagram. On this side we have a computer representation of N1, and on this side N2. I know, this is new, right? Now we're trying to keep it standard. And what we're going to have is, on the first packet sent across, we're going to have a sequence number assigned. In this case, it's 1024. When N2 receives that packet, as we showed on the earlier diagram, he's going to send an acknowledgement back, and it's called an ACK packet, and it has a number of 1025. Why 1025? All right. What it does is it takes the sequence number of the packet it received and adds one number. And what it's actually saying is, I have received everything before 1025, and I expect to see 1025 next. And then the next packet will come through with a sequence number of 2048. So why not 1025? That's what I expected to see next, right? He is able to send more than just one byte of information. This is measured in bytes in each packet. As you saw in the first one, those bytes were more than likely 1 to 1024. So 1024 bytes per packet. So on the next packet, simply sent the same number of bytes. 2048 is 1024 more than we had already received. So you send that on to N2. N2 then, as it did before, sends an acknowledgement of the last sequence number that it received plus 1. So this is what I expect to see next. And then you just see it happen again. This is a very simplified representation of how sequence packets and acknowledgement packets work together. Now, adding 1 to the last sequence number that I received, saying this is the sequence that I want to see next, is actually called forward acknowledgement. It's a great tool, but it really doesn't address the waste of bandwidth that I see here. Every time N1 sends a packet to N2, N2 acknowledges that packet. It doesn't look so bad here. I've only sent 3 packets. But remember that the throughput on your network can be millions of packets. Can you imagine doubling millions of packets and the effect that's going to have on your bandwidth? All right, so what's the answer to this problem? Here we have it. We have N1, again, and N2. This time, though, you see that N1 is transmitting 3 packets at one time, and they're all acknowledged by one ACK packet. Why does this work? It's called delayed ACK, or delayed acknowledgement. This is how it works. When I receive my first packet from N1 to N2, I start a timer. One of 2 things is going to happen. Either that timer is going to run out, or I'm going to receive N packets. Now, N packets is a number of packets that is in the code of TCP/IP that says, let's say for the sake of argument here, it's 3. It says, I start my timer when I receive the first packet. I am going to send the ACK when I receive 3 packets in total, or this timer goes off. The bandwidth benefits of deploying a delayed acknowledgement tactic are pretty obvious. I can send a group of packets and then I'll have one acknowledgement coming back acknowledging this whole group rather than having an acknowledgement on a per packet basis. All right, this gives you a really good idea of how packets are traded in a connection-oriented protocol. But you got to keep something in mind. By definition, connection-oriented protocols have a formal opening and a formal closing to every conversation or trade of packets that takes place. This slide has diagrams representing both the opening and the closing of a connection-oriented conversation. Let's start with the opening. In TCP specifically, the opening is called a three-way handshake. That is because it consists of three packets. The first starts at the sender, and it's a SYN packet, which is short for synchronized. And then the receiver sends back his own synchronized packet and an ACK packet. And then finally, N1, or the sender, sends an ACK packet. Let's look at this in more detail. When this SYN packet goes across, what I'm really saying is, can I talk to you? Again, it's pretty formal. So N1 is asking N2, can I talk to you? N2's response is kind of corny, but this is how it happens. He says, can I talk to you? Oh yeah, and by the way, yeah, you can talk to me. So that's the SYN and the ACK, and they're combined in one packet. And then finally, N1 says, yeah, you can talk to me. Now we have a setup that says all transfers can take place in the body of our conversation because we've had a formal opening. From here on out, we would trade packets as we talked about in the earlier parts of this session. N1 could send a bulk of packets to N2, which would acknowledge the entire bulk with one ACK packet, and N2 could do the same. It'll send transmitted packets back to N1, and it would acknowledge those packets with one acknowledgement. At some point, though, we're going to want to finish this conversation. When that happens, we will invoke our formal closing. Let's take a look at it. N1 is going to start by sending a FIN packet to N2. FIN is short for a finish packet. Then N2 is going to send an acknowledgement packet back, and it's going to follow that with a FIN packet of its own, and N1 would send an acknowledgement back. So let's go a little deeper and find out what we're saying here. N1 in its FIN packet is saying, I'm done talking. N2, not as corny as the startup, is going to say, okay, sounds good. And then he has the option of closing this connection. Now, when I say option, this doesn't have to happen. And the reason for that is what's called half-close functionality in TCP. Because N1 said, I'm done talking, N2 can simply say, okay, I'm not listening to you anymore, but he can continue to send packets to N1. So if he's not done with whatever process he's trying to invoke for N1 in this specific protocol, he continues up to the point that he wants to close the connection. And you will see this in a lot of captures if you have a sniffer. Then at the time that he wants to close the connection, he simply sends a FIN, again saying, I'm done talking, and N1 will say, okay. And because both are done at this point, now we have a true close. Before that, we had a half close. At this point, the session is terminated completely. So if N1 thinks, yo, you know what, I had something more to say, it's not just a matter of jumping to the middle here and starting to transfer data back and forth. You have to start all over, and he starts with the three-way handshake to N2, and then moves into the data transfer. Now that you know the basic data flow in a connection-oriented protocol, you can understand why different protocols use connectionless versus a connection-oriented method. Sometimes the data is so trivial it can be trusted to the network. Other times it needs to be watched and acknowledged as it traverses the network. As I said, that's the basic flow. Now we're going to look at some tools that will help us control that flow to our advantage. The first tool is also the easiest to explain. It's buffering. As we had in our earlier example, N1 sends 3 packets over to N2. N2 acknowledges those packets. Keep in mind that an acknowledgement means that we've received the packets. It's not N2 saying, I've processed these packets, but I've received them. So where are they? There's a finite piece of memory on N2 that is used to temporarily store these packets until they can be delivered to the CPU for processing. That's what buffering is. Continuing with that scenario, though, N1 has sent 3 packets over, each with 1,024 bytes in each. So let's say that that was all the finite memory we had available on N2. N2 still acknowledges those 3 packets because indeed it did receive them. But now if N1 sends another packet across of 1024 bytes, what's going to happen? There's no room at the end, essentially, so this packet will get discarded. Losing a packet isn't a good thing, but we have to realize that in a networked environment like this is, we are going to lose some, so it's not that big of a deal. But let's say that your CPU is being held hostage by a process on N2 that's not going to let go in the near future. N1 has sent a number of packets across the wire and received an acknowledgement, so it feels comfortable with sending more. Remember, losing 1 or 2 packets wasn't a big deal, but network throughput will allow N1 and many other N computers to send you data across the network that will arrive at N2 to find a finite buffer being full, and all those packets will be discarded. Now that's a problem. How do we solve that problem? Glad you asked. I just so happen to have a tool right here, windowing, that's going to help us do exactly that. To understand the effects of windowing, we're going to have to take a step back. Remember, before we were able to transmit data across from N1 to N2 on a connection-oriented method, we had to have a three-way handshake that set up this process. It was an official and formal opening. In that handshake, N2 told N1, I have a buffer, this finite buffer, I have enough space to hold 3072 bytes of data. So N1 said, fine, I'll transmit 3072 bytes of data to you. Now something happened in the time that N2 said this is what I can handle and the time that these packets arrived at his doorstep. Again, the CPU could have been held hostage and it can't process the data. So all of this sat in the buffer space. Now it's full. In this acknowledgement packet going back, we'll have a new field, and that field will be a window field. And because this is full, that window field can be set to 0. Now this stops N1 from sending any other packets to N2 because he understands I have no room to process these. So it seems that N1 is stuck. It just got word from N2 that its window size is 0, don't send me any more data. So it wouldn't be smart for N1 to send data across here saying, are you ready yet? Are you ready yet? At periodic intervals. So what do? The answer is in the Windows update. Let me explain what that is. We have the same diagram here, N1 conversing with N2, the buffer's full, N2 says I've got a window of 0. But now what N2 does is it waits an amount of time for this buffer to be free, and then it sends what's called a Windows update. Notice that the ACK is still 3073. That doesn't change. But the window size has changed. Now it's 3072 because I can accept data into my buffer because it's free. I didn't want to interrupt the flow of our diagrams, but we have to stop here and understand that what we're doing now is actually a variation of the tool we called windowing. With basic windowing, N2 can announce to N1, I have a window of 3072 bytes. N1 can announce the same to N2. And for the life of this conversation, they have to assume that that window is open constantly and that they can transmit data across. The moment that we were able to fluctuate our window and send this ACK with a window of 0, and then a window update with a window of 3072, we moved into the variation called sliding windows. So it seems that we have all our bases covered. We have 2 tools for flow control. The first was buffering, as you see here, and the next was sliding windows. Not just windows, but sliding windows. This seems like it'll allow N2 to talk to N1, but at the same time hold multiple conversations with N4, N6, and N7, any host on the network, and not discard packets. That's mostly true, but let me give you one more scenario. What we're going to find here is N1 communicating to N2, as in the other scenarios, and we're going to start with the three-way handshake. During the formal establishment of this conversation between N1 and N2, N2 advised N1 that it has a window available of 3072 bytes. Again, that's based on the finite buffer that is available on this PC. There's a problem though. N2 is correct in saying this is how much buffer space I have available, but it doesn't know about the network between N2 and N1. And in this case, we have a couple of routers with a slow WAN link. Why is this a problem though? The reason is this router acts just like a PC does in respect to having a buffer on each interface that is finite and it can only store so much data before it gets processed through the router. So in this case, N2 told N1, I can accept 3072 bytes of data, and N1 will transmit that in 3 packets. So let's say the 2 packets get to the router, and they're being stored in the buffer here. They fill the buffer. Because this WAN link is so slow, they're going to stay in the buffer for a period of time. The 3rd packet comes in and is discarded because there's no more room in the buffer. Now we see where we're going to get discarded packets, not so much because of the fault of N2, but the fact that N2 advertised a window to N1 that the network can't support. All right, I got to take a reality break because I know it sounds really ridiculous to say that 2 small packets are going to saturate the buffer of a router and then the 3rd packet will come in and be discarded. While I understand that a buffered router is much larger than this and it would take many more hosts with a higher throughput to make this happen, I simply want to get the concept across of what we're dealing with and the tools that are used to avoid these types of effects. Now back to flow control. The tool we're talking about now to overcome this is slow start. This is what's going to happen. When N2 advertises a window size, N2 is having to guess at the network between N1 and N2. And it simply doesn't scale. It's not a good idea. So with slow start, we create a new window. It's called a congestion window on N1. This is what N1 does. In the initial data transfer, it's going to send 1 packet to N2. As N2 acknowledges that packet, N1 is going to grow this window, the congestion window, to 2 and allow itself to transmit 2 packets this time. You can see that slow start helps us avoid having retransmitted and dropped packets because of buffers along the internet path being full, and it also saves us from having to wait on a window update to say now we can send data. But there's another point that we have to address. The growth that we're seeing here is an exponential growth. I send 1 packet to N2. As it gets acknowledged, this congestion window grows to 2. Now I can send 2. As they get acknowledged, the congestion window is going to grow to 4. Send 4, those are acknowledged, 8. And this will just keep on going, and it's going to grow pretty quickly. You got to keep in mind that we still have a window from N2 of 3,072 bytes that it can accept. This has been factored into the slow start algorithm, because basically it says, I will compare the congestion window, and I will compare the window that's advertised by N2. Whichever is smallest is the one that I'm going to use to govern how much data I can send across to the distant end. We have covered 3 very good tools that allow us to control the flow of data on connection-oriented protocols. Let's not kid ourselves though. There will be times that packets are discarded and lost in the middle of our transmission, so we have to have a very solid error recovery process. The first step in the error recovery process under the TCP/IP protocol is adaptive retransmission. This tool is actually very effective in its simplicity. Essentially, N1 transmits 3 packets to N2. As we know, in the sequencing, when we acknowledge the last sequence accepted plus 1. So if the acknowledgement is 2049 here from N2, it means that it received the first and the second packet. But it makes no mention in this acknowledgement of the 3rd packet. And because that's true, as soon as N1 transmitted these packets, it started a timer. It said, if I don't get an acknowledgement on these packets in a certain amount of time, I'll retransmit. And so what happened here is the acknowledgement came for 2049, it never came for 3072, and it simply retransmitted the packet across to N2. Let's move this tool out of this simplified scenario and into a real-world situation. I have a router between N1 and N2 now. When these first 2 packets were transmitted, they made it through to N2. This 3rd packet was stopped due to congestion at this interface. Now the fact that my retransmission timer right here is going to run out and I send another packet does not help this congestion. Now we said real world, so actually it's not 1 packet. N1 is going to transmit thousands of packets or retransmit thousands of packets per second to this interface that is already suffering from congestion. It just doesn't sound like the right answer. What is the answer? In the case of TCP/IP, it's congestion avoidance. Basically put, it's slow start with a twist. What's the twist? Slow start was at the beginning of a conversation. In congestion avoidance, this is going to happen whenever we're having a problem. So it can be in the middle of a session. There are other differences between congestion avoidance and slow start, but they're beyond the scope of this lesson. In this nugget, we identified differences between connectionless and connection-oriented methods of transmission. Then we studied the effects of flow control tools, and we ended up with a look at error recovery. I hope this has been informative for you, and I'd like to thank you for viewing.